Right now, lying there in the dark, you feel certain of one thing: that time is passing, that the universe is out there ticking forward in lockstep with you, one shared second at a time, everywhere, for everyone. That feeling is the most convincing illusion physics has ever caught in the act. Here is what you were never told. The universe itself does not experience time flowing at all. Not slowly, not quickly, not in any direction. There is no cosmic clock. There is no universal now shared by you and a star 10,000 light years away. Two people standing perfectly still, an arm's length apart from each other in this very room, can disagree about which distant events are happening at this exact instant, and physics says both of them are correct. Not approximately. Not as a rounding error, permanently, unresolvably correct, with nothing in the universe able to settle the argument. Einstein worked this out in 1905, almost as a side note buried in a longer paper, and it quietly dismantled the idea that time flows for the universe the way it seems to flow for you. Tonight, that is exactly what we are going to take apart together, piece by piece, until you understand what the universe is actually doing instead of ticking. Get cozy. Hit subscribe if you're new here, because by the end of this, now is never going to sound simple again. Let's slowly ease into this, the moment that isn't there. Try something simple before we go any further. Try to locate the present moment, not describe it, not define it in words, just point at it the way you might point at a chair. You will find this is harder than it sounds. By the time you have finished forming the thought this is now, the moment you were pointing at has already slipped behind you, replaced by another one, which is itself already gone by the time you notice it. The present does not hold still long enough to be examined. It behaves less like a place you can stand and more like the edge of a wave, always arriving, never staying. Most people never notice this, because most people never try. You live your whole life inside the present tense without once needing to ask what it actually is, the same way a fish presumably lives its whole life in water without needing a word for wet. The present feels less like an idea and more like the stage on which every other idea gets performed. Memory happens in the past. Anticipation happens in the future. But experience, actual raw experience, only ever happens now. That seems, on the face of it, to be the single most secure fact available to a conscious being. Whatever else you doubt, you cannot doubt that something is happening to you at this moment. Here is the part that should unsettle you. Physics has spent more than a century quietly proving that this feeling, however overwhelming it seems from the inside, describes nothing that exists in the structure of the universe. Not approximately nothing, not almost nothing. Nothing. There is no experiment, no equation, no observation in the entire history of physics that has ever located a universal present moment. Every time physicists have gone looking for the now that the whole cosmos supposedly shares, they have come back empty-handed, and eventually they stopped looking, because the theory itself explained why the search was doomed before it began. To understand how strange this really is, you have to go back to the picture of time that came before Einstein, the picture that Isaac Newton wrote into the foundations of physics in 1687, and that, frankly, most people still carry around in their heads without knowing it. Newton described time as something absolute. He wrote in the Principia that absolute, true, and mathematical time, of itself and from its own nature, flows equably without regard to anything external. Read that sentence slowly, because it is doing an enormous amount of work. Newton is not just saying that time passes. He is saying that it passes the same way everywhere, for everyone, regardless of what anyone is doing, regardless of where they are standing, regardless of how fast they are moving. In Newton's universe, there is a single master clock ticking away somewhere behind the scenery of reality, and every other clock, every heartbeat, every falling apple, every orbiting planet is simply reading off a local copy of that one true time. This picture is intuitive because it matches everything you have ever personally experienced. When you talk to a friend on the phone, you do not for a second entertain the idea that the two of you might be experiencing different presents. You assume, correctly as far as your daily life is concerned, that whatever moment you are in, they are in it too. Newton's absolute time is not a strange, exotic idea imposed on you by a textbook. It is the ordinary, unexamined assumption baked into the grammar of every language ever spoken. It is why we have a word like meanwhile, and for more than 2 centuries, nothing challenged it. Newtonian mechanics described the motion of planets, the fall of apples, the swing of pendulums, and the tides of the ocean with spectacular success, and buried invisibly inside every one of those successful calculations was the assumption of a single shared now, ticking uniformly across the entire universe, unquestioned because it never needed to be questioned. The predictions worked. Nobody had a reason to look underneath them. The crack appeared, as these things so often do, somewhere nobody was looking for it, in the behaviour of light. In the 1860s, the Scottish physicist James Clerk Maxwell wrote down a set of equations describing electricity and magnetism, and buried inside those equations was a strange, almost throwaway prediction. Light, according to Maxwell's mathematics, should travel at a fixed speed, and that speed should not depend on how fast the source of the light was moving or how fast the person measuring it was moving. Everyone, no matter their motion, should measure the same number. This should have been a minor technical curiosity. Instead, it was a quiet contradiction sitting at the heart of physics, because everything else about motion in Newton's universe worked by simple addition. Throw a ball from a moving train and the ball's speed, measured by someone standing on the platform, is the train's speed plus the throw's speed. That is common sense, and it had never once failed a test. But light, according to Maxwell, refused to play by that rule. However fast you chased it, it would not slow down relative to you. However fast you ran toward its source, it would not speed up. It was, in a sense that nobody in the 19th century quite knew what to do with, the same for everyone. Physicists at the time assumed there had to be a hidden medium responsible, some invisible substance filling all of space through which light waves rippled the way sound ripples through air, and that this medium, nicknamed the luminiferous ether, would give the universe back its Newtonian footing. If the ether existed, then the Earth's motion through it could in principle be detected, the way you can feel a headwind on a moving train even with your eyes closed. In 1887, Albert Michelson and Edward Morley built an instrument sensitive enough to detect exactly that headwind, splitting a beam of light in 2 directions and looking for the faint difference in speed that the Earth's motion through the ether should have produced. They found nothing. Not a small effect. Not a difficulty in isolating the signal from noise. Nothing at all, in every direction, at every time of year, no matter how the experiment was oriented. The result was so quietly devastating that physicists spent the better part of 2 decades trying to explain it away rather than accept what it seemed to be telling them, which was that light simply does not behave like a wave in a medium at all, and that the entire concept of a fixed, universal backdrop against which motion could be measured absolutely might not exist. This is the moment worth sitting inside for a while, because it is the hinge on which the rest of tonight turns. A single stubborn experimental result, repeated and refined for years, was quietly telling physics that the speed of light was not going to bend to accommodate anyone's motion, and that something else, something nobody had thought to question, was going to have to give instead. Newton's absolute time, the single shared now flowing equably for everyone everywhere, had survived 200 years of scrutiny by never once being directly tested. The Michelson-Morley experiment did not test it directly either. It simply removed the last comfortable place for it to hide. It would take a 26-year-old patent clerk in Switzerland, working through the implications on quiet afternoons at his desk, to realize what had to be sacrificed to make the numbers agree with what Michelson and Morley had actually measured. And what he sacrificed, without any hesitation and without any apparent understanding at the time of how far the consequences would reach, was the very thing every human being has ever assumed was the safest fact available to them. The idea that there is a single present moment shared by everyone ticking forward together. That is where we are going next. Part 2. The Clerk Who Broke Meanwhile. In 1905, Albert Einstein was not a professor. He held no laboratory position, no research fellowship, no university salary. He worked 6 days a week at the Swiss Federal Patent Office in Bern, examining applications for electromagnetic devices, deciding which clever inventions were plausible and which were quietly nonsense. It was, by every account, a decent job for a man who could not get an academic post, and it left him with something surprisingly valuable: quiet afternoons in which nobody expected him to be doing anything except reading patents. He spent a great many of those afternoons thinking instead about light. He was not trying to overthrow Newton. He said as much himself later, describing the process almost as an accident of stubbornness. He had simply decided to take Maxwell's equations seriously, to actually believe the strange prediction sitting inside them, that the speed of light is the same for every observer, no matter how they are moving. Everyone else treated that prediction as a puzzle to be explained away by some hidden mechanism, some undiscovered property of the ether that would eventually restore the comfortable Newtonian picture. Einstein, instead, asked a different question. What if the prediction is simply true? What has to give elsewhere in physics to make that possible? The answer he arrived at, worked out in a paper titled On the Electrodynamics of Moving Bodies and published in the journal Annalen der Physik, is not long. It contains no laboratory apparatus, no original experiment of its own, nothing but careful reasoning laid out with an almost eerie calm. And somewhere in the middle of that calm reasoning sits a thought experiment so simple that a child could follow it, and so devastating that it quietly dissolved the concept of a shared universal present for everyone who understood it properly. Picture an embankment running alongside a railway track. Standing on the embankment is an observer, motionless relative to the ground. A long train moves past at a steady speed, and inside that train, near its exact midpoint, sits a second observer. Now imagine 2 bolts of lightning strike the track at the same instant, one at the front of the train's position and one at the back, and imagine, crucially, that both strikes are equidistant from the observer standing on the embankment. Because light from both strikes has the same distance to travel to reach that stationary observer, and because light travels at a fixed, unchanging speed, the 2 flashes arrive at the embankment observer's eyes at exactly the same moment. From where that person is standing, the 2 lightning strikes were simultaneous. This is not controversial. It is exactly what you would expect, and it matches everything Newton would have told you. Now consider the observer riding on the train. At the instant the 2 flashes occur, That observer happens to be passing directly alongside the embankment observer, so the two of them share, for that one instant, the same location. But the train is moving. By the time light from the front strike and light from the back strike reaches the midpoint of the train has continued forward, carrying its passenger closer to the point where the front strike occurred and farther from the point where the back strike occurred. The light from the front strike, therefore, has less distance to travel to reach the train's passenger, and the light from the back strike has more. Since light travels at the same fixed speed for this observer too, the flash from the front arrives first, and the flash from the back arrives second. From the passenger's point of view, the two lightning strikes were not simultaneous at all. The front one happened first. Here is where the entire architecture of the classical universe quietly buckles. Both observers did everything correctly. Neither of them made a measurement error, neither of them used a faulty instrument, and neither of them is confused about what they saw. The embankment observer is completely correct that the strikes were simultaneous. The train passenger is completely correct that they were not. There is no experiment either of them could run, no more careful measurement, no cleverer instrument that would resolve the disagreement in either direction, because there is nothing to resolve. Both descriptions are true. Simultaneity, the very idea of two distant events happening at the same time, turns out not to be a fact about the universe at all. It is a fact about the observer, about their state of motion, entangled inextricably with the position from which they are asking the question. Sit with the size of that for a moment, because it is easy to let it slide past as a clever puzzle rather than the seismic event it actually is. Every single time you have ever used the word now to describe something happening somewhere else, every time you have said right now, on the other side of the world, or imagined a distant star existing at this moment, you are smuggling in an assumption that Einstein's thought experiment shows has no foundation whatsoever. There is no fact of the matter about which distant events are happening at the same time as the event you are experiencing. Not because we lack the technology to check, because the question itself, taken at face value, does not have a single answer waiting to be discovered. It has as many answers as there are observers in as many states of motion, and every single one of them is correct. This is what physicists call the relativity of simultaneity, and it is arguably the single most underappreciated result in the entire history of science, precisely because it sounds, on first hearing, like a technicality. It sounds like something that only matters for objects moving at outlandish speeds, spaceships and particle accelerators, nothing that could possibly touch your actual life. That impression is wrong, and it is wrong in a way that is worth being precise about. The effect is not absent at ordinary speeds. It is simply small, buried under enough zeros that no human sense could ever register it. Two people passing each other while walking down a street are, in the strictest and most literal sense that physics can define, disagreeing about which distant events are simultaneous with the moment they pass. The disagreement, for anything beyond a modest distance, might amount to a fraction of a second, entirely undetectable, utterly irrelevant to anyone's day. But it is there. It does not switch on at high speed and switch off at low speed. It is a feature of the geometry of the universe itself, present in every relative motion, at every scale, all the time, whether or not anyone is moving fast enough to notice. And once you accept that even two people walking past each other on a sidewalk cannot, strictly speaking, agree about what is happening on the far side of the galaxy right now, the entire idea of a universal present moment, a single now shared by the whole cosmos, simply has nowhere left to stand. It is not that the universal now is hidden somewhere, waiting for better instruments to reveal it. It is that the universal now was never a coherent concept to begin with. It was an assumption inherited from a picture of physics that worked beautifully for falling apples and orbiting planets and simply never got tested against the behavior of light, because nobody had reason to test it until Maxwell's equations and the Michelson-Morley experiment quietly forced the question. What makes this even stranger, and what we are going to spend the rest of tonight unpacking, is what happens once you take the relativity of simultaneity seriously and ask what it implies about the structure of the past and the future themselves. Because if two observers can disagree about which distant events are happening now, then it turns out they can also, under the right circumstances, disagree about the order in which distant events happened at all. Event A might occur before Event B according to one observer, and after Event B according to another, with neither of them making any error whatsoever. There is a strict and important limit to how far this can go, a boundary the universe absolutely refuses to let anyone cross, and understanding exactly where that boundary sits, and why it exists at all, is going to take us directly into the geometry that replaced Newton's absolute time, a structure called space-time, first described not by Einstein himself, but by the very mathematician who, 3 years earlier, had dismissed Einstein's paper as the mathematically unremarkable work of a former student he privately considered somewhat lazy. That correction and the geometry it produced is where we are going next. Part 3. The mathematician who saw the shape of it. Hermann Minkowski had taught mathematics at the Federal Polytechnic in Zurich, and among the students who passed through his classroom in the late 1890s was a young man who, by Minkowski's own later admission, had not particularly impressed him. Minkowski reportedly described Einstein to colleagues as a lazy dog, someone who skipped lectures, who did not apply himself with the discipline Minkowski expected of a serious student of mathematics. It is one of the small ironies of this story that the very physics this lazy dog produced a decade later would occupy the final years of Minkowski's working life, and that Minkowski himself would become the person who gave that physics its enduring shape. When Einstein's 1905 paper began circulating among physicists, most of the response fell into one of two categories. Either it was dismissed as an elegant but essentially cosmetic reworking of Lorentz's earlier equations, mathematics dressed up with philosophical flourishes about clocks and rulers, or it was quietly set aside as too strange to be worth serious engagement. Minkowski's response was different, and it took him a few years to fully develop it. He looked at the equations Einstein had derived, the equations describing how lengths contract and clocks slow for observers in relative motion, and he noticed something that Einstein himself had not emphasized. These equations were not simply a set of rules about how measurements change. They were the signature of a geometry, a specific, definite, four-dimensional geometry, and once you saw it that way, the strangeness of relativity stopped looking like a collection of separate paradoxes and started looking like the entirely predictable consequence of a single underlying shape. On the 21st of September 1908, Minkowski stood up at a conference of German scientists in Cologne and delivered a lecture that opened with one of the most quietly audacious sentences in the history of physics. Henceforth, he said, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. He was not offering a helpful metaphor. He was making a precise claim that the three dimensions of space and the single dimension of time are not two separate kinds of thing that happen to appear together in physical descriptions. They are four coordinates within one combined structure, a structure he called the world, and which physicists ever since have called space-time. To understand what this actually buys you, it helps to go back to something you already know without ever having thought of it as strange. In ordinary geometry, if you walk 3 meters east and then 4 meters north, you have not walked 7 meters from your starting point. You have walked 5. Because distance in a plane obeys the Pythagorean rule, the sum of the squares of the two legs equals the square of the straight line distance between them. This rule is roughly 2,500 years old, and it is so deeply embedded in how you picture space that it barely registers as a rule at all. It is simply how distance works. Minkowski showed that space-time has a rule exactly like this one, with a single world-altering difference. To find the separation between two events, not two places, but two happenings, each with a location and a moment, you take the time part and the space parts and combine them, but instead of adding every term the way the Pythagorean theorem does, you subtract the space terms from the time term. 1 minus sign, sitting where every geometry devised before 1908 had put a plus. That single character is the entire content of special relativity. Every strange result that has ever been attributed to Einstein, the disagreement about simultaneity we spent the last part unpacking, the slowing of moving clocks, the contraction of moving lengths, all of it falls directly out of that 1 minus sign, worked through carefully. And this combined quantity, time squared minus space squared, has a property that neither time alone nor space alone possesses. Every observer agrees on it. Two people moving at different speeds relative to each other will disagree completely about how much time passed between two events, and they will disagree completely about how much distance separated them. But when each of them takes their own disagreeing numbers and runs them through Minkowski's formula, they arrive at exactly the same answer. Physicists call this quantity the interval, and it is the closest thing this universe possesses to an absolute, observer-independent fact. Time is not absolute. Space is not absolute. The particular combination of the two that Minkowski identified is absolute, and it was sitting there, invisible, the entire time anyone had assumed time alone was the fixed backdrop against which everything else moved. This is the geometrical structure that finally explains something the previous part left dangling. We established that two observers in relative motion can disagree about which distant events are simultaneous, and that disagreement is real, not an illusion produced by delayed signals or measurement error. A natural and unsettling question follows immediately from that fact. If simultaneity is not absolute, if observers can disagree about which of two events happened first, is there anything preventing that disagreement from spiraling out of control? Could one observer see you strike a match before you ever picked it up? Could cause and effect themselves become simply a matter of perspective, with the universe offering no fixed answer about what led to what? The geometry Minkowski built answers this question precisely, and the answer is both a genuine relief and a genuinely strange boundary. Picture, for any single event, all of the light that could ever reach it from the past, and all of the light it could ever send out into the future. Drawn out in a space-time diagram, this traces two cones meeting at a point, one opening into the past and one opening into the future, together forming what is called the light cone of that event. Everything inside the future cone represents events that this one could, in principle, cause, events reachable by a signal travelling no faster than light. Everything inside the past cone represents events that could, in principle, have caused this one. And everything outside both cones, off to the sides, in a region physicists call space-like separated, is neither in this event's past nor its future in any absolute sense at all. Here is the crucial distinction, and it is the resolution to the worry that should have been building since the last part. For any two events that are time-like separated, meaning one of them lies inside the other's light cone, every observer in the universe, no matter their speed or direction of motion, agrees completely on which one happened first. There is no ambiguity whatsoever. If a match strike could plausibly cause a subsequent fire, every observer everywhere agrees the strike came first and the fire came second. Cause and effect are absolutely universally protected in this region of the geometry. The relativity of simultaneity, the disagreement about ordering that felt so destabilizing a moment ago, only ever applies to events that are space-like separated, events too far apart in space for any signal, even one travelling at the speed of light, to have crossed the distance between them in the time available. For those events, and only those events, different observers can legitimately disagree about which happened first, because no possible cause and effect relationship could exist between them in the first place. Nothing was ever going to travel from one to the other fast enough to connect them. The universe permits disagreement exactly where disagreement is harmless, and forbids it with absolute rigidity everywhere causality could actually be threatened. This is a genuinely elegant piece of architecture, and it is worth pausing to appreciate what it means for the picture we are slowly building tonight. The universe is not a chaotic free-for-all in which any observer can rearrange events however they like. It is a structure with a very precise, very carefully enforced boundary between the region where ordering is absolute and the region where it is genuinely, permanently a matter of reference frame. And the boundary itself is drawn by light. The speed of light is not simply the fastest thing that happens to exist. In Minkowski's geometry, it is the edge of the cone itself. The dividing line the entire structure is built around, the conversion factor between the space directions and the time direction that makes the whole geometry hang together. What this means, stated plainly, is that the present moment you feel so certain of is not a slice of the universe at all. It is not a plane sweeping through space-time, carrying every galaxy and every person forward together in lockstep. There is no such plane. There cannot be one, because different observers, moving at different speeds, slice the four-dimensional structure of space-time at different angles, and each of those slices, each of those personal now moments, cuts through a completely different set of distant events as simultaneous. Your now and the now of someone moving relative to you are not offset copies of the same slice. They are different slices entirely, tilted against each other by an angle set by your relative velocity, agreeing only within the narrow cone of events close enough and slow changing enough that the disagreement never becomes visible. And once you have accepted that the present is not a universal slice, but a personal, angle-dependent one, an entirely new question opens up, one that Einstein himself found genuinely troubling later in his life, in ways that go beyond the mathematics we have covered so far. If every observer has their own slice, their own now, then what exactly is left of the past and the future? Are they simply regions not yet sliced through, waiting somewhere ahead and behind? Or is there a stranger possibility, one that a letter Einstein wrote in the final weeks of his own life suggests he had come to believe that the past, the present, and the future are not stages an object passes through at all, but are, in some sense, that ordinary language struggles badly to capture. All equally and permanently real, laid out together in a single unchanging structure that nothing actually moves through. Part 4. The letter that would not let go. In March of 1955, Albert Einstein was 76 years old and living out his final weeks in Princeton, New Jersey. His health was failing. He knew by his own account that he did not have long left, and in the middle of that final stretch of his life, he received word that his oldest and closest friend, a man named Michel Besso, had died. The friendship between Einstein and Besso stretched back to their years together in Zurich, decades before either of them had any idea what Einstein's quiet afternoons at the patent office in Bern would eventually produce. It was Besso, in fact, who Einstein later credited as the one person with whom he could genuinely discuss the ideas that became special relativity while he was still working them out. The one sounding board patient enough to listen to a young man think aloud about light and clocks and simultaneity before any of it had a name. Their correspondence continued for the rest of Einstein's life, decades of letters passing back and forth, and when Besso died just weeks before Einstein himself would, Einstein wrote to Besso's surviving family. The letter is short, and one sentence from it has since become one of the most quoted lines in the popular literature of physics, repeated so often that it risks becoming a slogan rather than what it actually was, which is a dying man's genuine attempt to say something true and consoling using the only framework he had ever fully trusted. Now he has departed from this strange world a little ahead of me, Einstein wrote of his friend. That means nothing. People like us, who believe in physics, know that the distinction between past, present and future is only a stubbornly persistent illusion. Read that sentence slowly, because it deserves more weight than it is usually given. Einstein was not offering vague comfort in the way people often do at moments like this, reaching for a soft phrase because the truth feels too painful to say plainly. He was doing something much stranger and, in its own way, much more remarkable. He was telling Besso's grieving family that the physics he had spent his life building, the very same geometry we spent the last two parts constructing together, actually implies something specific and startling about what it means for a person to have died. Not a metaphor, not a gentle turn of phrase borrowed from religion or poetry. A direct claim made by the person who understood the structure of space-time better than anyone alive, that the ordinary picture of the past being gone and the future being not yet real is, in his considered opinion, an illusion, and a stubborn one at that, precisely because it refuses to go away even once you know better. To understand what Einstein actually meant by this, and why it follows with genuine rigour from the geometry Minkowski built, rather than being a piece of comforting philosophy dressed up in scientific language, you have to go back to the light cone structure from the last part and ask a question that sounds almost childishly simple. Where, exactly, in the four-dimensional structure of space-time, is the boundary between what has happened and what has not yet happened? In the everyday picture, the one built into the grammar of every language, this boundary is obvious. It is the present moment, and it sweeps forward uniformly, turning future events into present events and then into past events, at the same steady rate for everyone, everywhere. This sweeping boundary is sometimes called, in philosophy departments rather than physics departments, the moving spotlight. The idea that reality is somehow illuminated moment by moment as this universal boundary passes over it, with everything behind the spotlight fixed and settled into the past, and everything ahead of it still open, still undetermined, waiting to be decided. We have already established, carefully and step by step, that this picture cannot be correct, because it requires exactly the thing the relativity of simultaneity rules out: a single, universal present moment shared by every observer everywhere. There is no such moment. Different observers, moving at different velocities, slice space-time at different angles, and their personal now moments do not agree about which distant events count as present. If there is no universal now, there is no universal moving spotlight, and if there is no universal moving spotlight, then there is nothing in the actual mathematics of space-time that plays the role of the sweeping boundary the everyday picture depends on. What is left, once you take that seriously, is a structure sometimes called the block universe, and it is worth being precise about what this phrase does and does not mean, because it gets garbled constantly in popular explanations. The block universe view does not say that time is an illusion in the sense of not existing at all. Time, in this picture, is entirely real. It is a dimension, every bit as real as the 3 dimensions of space, and events are genuinely spread out along it, earlier and later, exactly the way objects are spread out at different positions in space. What the block universe view denies is not the reality of time, but the idea that there is anything privileged about the present moment, anything that makes now metaphysically different in kind from any other moment along the timeline. In this picture, your birth and your death are not events that reality passes through, one after the other, extinguishing each as it goes. They are simply locations, coordinates in the 4-dimensional structure, no more transient or provisional than the location of your childhood home is transient just because you are not currently standing in it. This is what Einstein meant, and it is why he felt entitled to say to a grieving family that the distinction between past, present and future is only a stubbornly persistent illusion. In the geometry he had spent his life building, Michel Besso's entire life, every moment of it from birth to death, does not cease to exist the instant his heart stops beating. It remains exactly where it always was, a fixed, permanent region of the 4-dimensional structure of space-time, no less real for the fact that Einstein's own personal light cone had, by March of 1955, moved past the point of Besso's death. Besso was not erased. He was, in the strict sense the geometry supports, still there, laid out along his own portion of space-time, in exactly the way a city you have already driven through is still there on the map even after your car has carried you somewhere else. There is a philosophical vocabulary that has grown up around this question, and it is worth knowing the terms, not because the labels change the physics, but because they help sharpen exactly what is and is not being claimed. The view that only the present moment is real, that the past has ceased to exist and the future does not yet exist in any sense at all, is called presentism, and it is, roughly speaking, the view built into ordinary language and ordinary intuition, the view almost everyone carries around without ever examining it, the view that the past and present are real and fixed, but the future remains genuinely open and undetermined, growing moment by moment as new events crystallize into fixed fact, is called the growing block view, and it has attracted serious philosophical defenders precisely because it tries to preserve some version of an open future while still respecting relativity's verdict about the reality of the past. And the view that the entire 4-dimensional structure, past, present and future alike, is equally and permanently real, with no moment more privileged than any other, is called eternalism, and it is, by a wide margin, the view most naturally suggested by the mathematics of relativity itself, which is exactly why so many physicists, following Einstein's lead, have found themselves drawn toward it, sometimes reluctantly. It is worth being honest about how uncomfortable this can feel, because there is a real risk in a video like this one of making eternalism sound like a tidy, settled conclusion that everyone in physics has simply accepted and moved on from. That is not quite the situation. The mathematics of special relativity does genuinely favour eternalism over presentism, because presentism requires exactly the universal simultaneous present moment that relativity shows does not exist. But physics describing a structure and physics settling the deeper metaphysical question of what it means for something to be real are not automatically the same achievement. And there remain serious, careful philosophers of physics who argue that some version of an open, growing future can still be reconciled with relativity, typically by locating the growth not in a universal present, but in something more local, tied to each observer's own light cone rather than to space-time as a whole. The debate is real, it is ongoing, and it has not been closed by a single equation, however elegant. What is not in serious dispute, however, is the narrower and in some ways more startling claim that started this entire part. There is no universal present moment sweeping through the cosmos, turning future into past at a shared, agreed-upon rate for every observer. That specific claim, the one Einstein was quietly relying on when he wrote to Besso's family, is not a matter of interpretation or philosophical taste. It follows directly and rigorously from the relativity of simultaneity, which we established in painstaking detail 2 parts ago using nothing more exotic than a train, an embankment, and 2 bolts of lightning. Whatever time actually is, and we are going to spend much of the rest of tonight circling that question from different directions, it is not a uniform tide lifting every event in the universe together, moment by shared moment, into and then out of existence. Something else entirely is going on, something the geometry describes with total precision and complete confidence, and something that human intuition evolved entirely within the narrow, slow-moving, everyday range of speeds where the relativity of simultaneity is too small to ever notice, was never built to feel. This raises an immediate and pressing question, one that anyone encountering the block universe idea for the first time tends to ask almost instinctively, and it deserves a full and careful answer rather than a dismissive wave of the hand. If the past and future are equally real, laid out permanently alongside the present in a fixed 4-dimensional structure, then why does it feel like time is passing at all? Why does the future feel open and undetermined, while the past feels fixed and unchangeable? Why do you remember yesterday, but not tomorrow? If nothing in the geometry itself distinguishes one moment as more real or more privileged than any other, where on earth does the powerful, undeniable, universal human sensation of time flowing actually come from? That question, more than any other, is the one this entire video has been building toward, and answering it properly requires leaving the geometry of special relativity behind for a while and turning instead toward a completely different branch of physics, one that has nothing to do with light cones or moving trains, and everything to do with something far more mundane and far stranger. The slow, one-directional, unstoppable process by which an egg breaks and does not unbreak, by which a cup of coffee cools and does not spontaneously reheat, by which every ordered thing in the universe drifts, given enough time, toward disorder. That process has a name, the second law of thermodynamics, and it is, as we are about to see, the closest thing physics has ever found to an actual arrow pointing through the block, even though the block itself, strictly speaking, contains no arrow at all. Part 5. The egg that will not unbreak. Push a cup off the edge of a table and you already know, without needing to think about it, what happens next. It falls, it strikes the floor, and it shatters into a scatter of ceramic fragments spread across the tiles. You have never once in your life seen the reverse. You have never watched scattered fragments gather themselves up off a floor, assemble seamlessly back into a cup, and leap upward onto a table. And here is the detail that should genuinely trouble you once you sit with it properly. Nothing in the fundamental laws of physics forbids that reversed sequence from happening. not softly discourages it, does not forbid it at all. This is one of the strangest and most persistently underappreciated facts in the whole of physics, and it deserves to be stated with total precision before we go any further, because it is easy to state carelessly and lose the point entirely. If you take the fundamental equations governing the motion of individual particles, whether you are working in Newton's classical mechanics, in Maxwell's electromagnetism, or in the quantum mechanics that eventually replaced both of them at the smallest scales, and you run those equations backward in time, they still work. They do not throw an error. They do not produce nonsense. A film of 2 billiard balls colliding on a table, played forward, shows one plausible sequence of events. Played backward, it shows a sequence that is equally, exactly, mathematically plausible according to the underlying laws. The individual laws of physics governing individual particles do not, on their own, contain any preference for one direction of time over the other. Physicists call this property-time reversal symmetry, and at the level of fundamental particle interactions, it holds almost perfectly, with one exceedingly small and exotic exception involving a particular kind of subatomic decay that we will come back to briefly much later. An exception so minuscule it plays no meaningful role in why your coffee cools rather than spontaneously boils. So if the fundamental laws do not prefer a direction, where does the obvious, undeniable, everyday direction of time actually come from? Why does the cup shatter and never unshatter? Why does the egg break and never unbreak? Why does milk stirred into coffee spread out into a uniform tan colour and never spontaneously separate back into a distinct white swirl? The answer has nothing to do with any single particle obeying any special rule. It has to do with numbers, specifically with staggeringly, almost unimaginably large numbers, and the statistics of what happens when you have enough particles interacting together that counting arrangements becomes the only thing that matters. Consider the shattered cup lying on the floor. There is exactly one way, or something close to exactly one way, for those particular ceramic fragments to be arranged such that they form an intact, unbroken cup. The number of ways to arrange those same fragments in some jumbled, broken, scattered configuration, on the other hand, is almost incomprehensibly larger. This is the whole of the insight, and it is worth letting it land in its full simplicity before we dress it up in more formal language. It is not that the universe has some deep preference for disorder, some rule written into its foundations insisting that broken states are more natural than whole ones. It is that there are overwhelmingly, catastrophically more ways to be broken than there are ways to be whole. And when a system evolves through its available states more or less at random, the odds of it wandering into one of the astronomically rare ordered configurations and staying there are so small that across any timescale you could ever actually witness, it simply does not happen. Physicists give a name to the number of ways a system's underlying details can be arranged while still looking the same at the level you can actually observe, and that name is entropy. A low entropy state is one where the number of underlying arrangements consistent with what you see is small, tightly constrained, special. A high entropy state is one where the number of underlying arrangements is enormous, generic, unremarkable. An intact cup is a low entropy arrangement of ceramic atoms. A pile of shards on the floor is a high entropy arrangement of exactly the same atoms. And the second law of thermodynamics, one of the most thoroughly tested and universally respected principles in the whole of science, states simply that in any isolated system, entropy overwhelmingly tends to increase over time, not because any law forces it to, because there are so vastly more high entropy arrangements available than low entropy ones that, left to its own devices, any system will almost certainly wander from a rare, special, ordered configuration toward one of the countless generic, disordered ones, and essentially never wander back. This is the arrow. Not a law forbidding the reverse, but a probability so extreme against the reverse that the distinction between forbidden and merely astronomically unlikely stops mattering to anyone who has to actually live inside the universe rather than merely calculate about it from outside. Ludwig Boltzmann, the 19th century physicist who did more than anyone to put this statistical picture on a firm mathematical footing, faced exactly this objection from his contemporaries. If the underlying laws are time-symmetric, they told him, then your statistical argument should apply equally well running backward as running forward, and it should be just as likely, by your own logic, that a broken cup on the floor spontaneously assembled itself moments ago as that it will remain broken moments from now. Boltzmann's answer, refined over years of debate, was essentially correct, and it points towards something genuinely profound about the structure of the entire observable universe, something that reaches far beyond broken cups and cooling coffee. If entropy really does tend to increase in both directions away from any given moment, purely as a matter of probability, then the only way to explain why we consistently observe a universe with a clear, one-directional arrow, low entropy firmly fixed in the past, and high entropy consistently increasing toward the future, is if the universe as a whole began at some definite starting point, in an extraordinarily special, extraordinarily low entropy state, not a typical state, not a generic one so improbable, so wildly atypical among all the states a universe with this much matter and energy could in principle have started in, that its very existence demands an explanation nobody has yet fully supplied. The physicist Roger Penrose attempted, decades later, to actually calculate how special that initial state must have been, comparing the volume of possible starting configurations that would produce a universe like ours against the volume of all configurations available in principle, and the number he arrived at is not merely large. It is a number so far beyond ordinary description that writing out its digits would exceed what could be physically inscribed using every particle in the observable universe as ink. The early universe, in other words, did not simply happen to have low entropy. It had entropy so improbably, so almost impossibly low, that its origin sits today as one of the genuinely open, unresolved mysteries at the foundation of modern cosmology, every bit as unsettled as the questions about dark matter or dark energy that occupy so much more of the public conversation. Here is where this connects back, with real force, to the question left hanging at the end of the last part. We established that the block universe of special relativity contains no built-in arrow, no privileged direction singling out the future as somehow different in kind from the past. The equations of relativity, like the fundamental equations of particle motion underneath thermodynamics, do not prefer one direction of time over the other, and yet you experience an overwhelming, unmistakable arrow every single day of your life. You remember yesterday, you do not remember tomorrow. You anticipate the future with uncertainty and recall the past with a settled, if imperfect, confidence. Photographs capture what has already happened, never what is about to happen. Every single one of these asymmetries, every one of them, without exception, traces back to entropy, to the fact that you exist inside a universe that began in an extraordinarily low entropy state and has been drifting toward higher entropy ever since. And that this drift, this statistical tendency, rather than any fundamental law, is the actual engine behind everything that makes the future feel different from the past. Consider memory itself, since it is perhaps the single most intimate and personal place this abstract cosmological argument reaches into your actual life. What is a memory, physically speaking? It is a particular arrangement of matter, most obviously the specific configuration of neurons and synaptic connections in your brain that has been altered by a past event in a way that persists afterward. For a memory to form, an event has to leave a physical trace, and leaving a trace is itself a process that increases entropy, converting some ordered potential into a slightly more disordered but now recorded state. This is precisely why you can remember the past and not the future. It is not a metaphysical mystery requiring some special theory of consciousness. It is a direct physical consequence of the fact that the entropy increasing arrow only permits traces to form pointing in one temporal direction. A photograph can only be a record of an event that has already increased the universe's entropy in leaving its mark. There is no physical mechanism, none, by which a photograph could record an event that has not yet happened, because doing so would require entropy to spontaneously decrease in exactly the coordinated, improbable way the second law rules out for all practical purposes. Your memory, in other words, the very faculty that makes you feel like a being moving forward through time rather than a static object embedded timelessly in a block, is itself nothing more than a local pocket of the same entropy gradient that governs shattered cups and cooling coffee. This is worth pausing on because it reframes the entire emotional weight of the question we have been circling all evening. You do not experience time flowing because time is actually flowing, in the sense of some universal cosmic tide sweeping the present moment forward through a fixed structure. You experience time flowing because you are a low entropy structure yourself. A remarkably ordered arrangement of matter, temporarily maintaining that order by consuming energy and expelling waste heat. A process that is itself, at every single step, increasing the entropy of your surroundings even as it locally sustains the order that lets you think, remember, and notice. You are not a passenger being carried along by time. You are, in a very real and physically precise sense, an entropy-increasing process embedded within a universe that started in an improbable state of order and has been draining toward disorder ever since. And your subjective sense of time passing is simply what it feels like, from the inside, to be one small local current within that much larger drain. There is an honest complication worth adding here before we move any further, because leaving it out would flatten a genuinely open and interesting question into something falsely settled. The entropy story explains beautifully why the past looks different from the future, why memories point one way and not the other, why cups shatter and do not unshatter. What it does not, by itself, fully explain is why you experience only a single instant of now at all, rather than experiencing your entire life, from birth to death, all at once. The way the block universe picture suggests is genuinely how you are laid out within space-time. The entropy gradient explains the direction of the arrow. It does not, on its own, obviously explain the existence of a moving present, a felt now, threading through that arrow one instant at a time. Some physicists and philosophers argue that once you properly account for the entropy gradient and the way memory and consciousness are built from it, moment by moment, the feeling of a moving present falls out naturally. An inevitable byproduct of being a certain kind of information processing structure embedded in a universe with this particular thermodynamic history. Others are considerably less convinced, and argue that there remains a genuine gap between explaining why the past feels fixed and the future feels open, and explaining why there is any experience now at all rather than a single, static. four-dimensional experience of the whole block simultaneously. This gap has a name in philosophy of mind, and it echoes almost precisely the gap Einstein himself admitted in conversation late in his life that physics had never managed to close. But whatever the final resolution of that deeper puzzle turns out to be, the thermodynamic arrow itself is not in question. It is one of the most rigorously tested principles in the whole of physics, confirmed at every scale from individual molecular collisions studied in laboratories to the large-scale thermal history of the observable universe reconstructed from the cosmic microwave background. And it delivers, at this point in tonight's journey, something genuinely valuable. It gives us a real, physically grounded, statistically certain arrow embedded within the timeless block universe of special relativity, without requiring any universal moving present, without requiring any single moment more real than any other, and without contradicting a single result Einstein and Minkowski established. The block does not move. But the block, as it happens, is not uniform. It is shaped from one end to the other by an entropy gradient running from an almost inconceivably improbable, tightly ordered beginning toward an ever more probable, ever more disordered future, and it is that shape, not any flow, that gives your life its unmistakable sense of direction. This still leaves an enormous and genuinely unresolved question sitting directly in front of us, one that will occupy the second half of tonight's journey. We have carefully separated two very different things that ordinary language collapses into a single word. There is the geometric structure of space-time itself, the block, timeless, containing past and future with equal reality, sliced differently by different observers, exactly as Einstein and Minkowski described. And there is the thermodynamic arrow, the entropy gradient running through that block, explaining why memory, causation, and the felt difference between past and future all point the same way. But neither of these, not the geometry and not the thermodynamics, has yet told us what a clock is actually measuring when it ticks, or why moving clocks measure less of it than stationary ones. A fact we have mentioned only in passing tonight, but which turns out to be the single most concrete, most laboratory-tested, most undeniable piece of evidence that time, whatever it ultimately is, behaves nothing like the uniform river of ordinary intuition. To understand that, we need to look directly at what a clock actually does, and follow that understanding all the way out to atomic clocks flown on commercial airliners, muons raining down from the upper atmosphere, and a cosmonaut who is, at this very moment, measurably younger than he has any right to be. That is where we are going next. Part 6. What a clock is actually counting. Ask someone what a clock does, and they will tell you, without much hesitation, that it measures time. Ask them to be more precise about what that actually means, and the conversation tends to stall because the answer feels too obvious to need explaining. A clock ticks, and time passes, and the ticks tell you how much of it has gone by. This description feels complete. It is not. It quietly assumes exactly the thing the last two parts have been slowly dismantling, that time is a substance flowing past a passive observer, and that a clock is simply a witness recording that flow, the way a rain gauge records rainfall without in any sense causing or participating in the weather. The geometry Minkowski gave us in Part 3 suggests something quite different, and once you take it seriously, it changes what a clock is in a way that has enormous, testable consequences. In that geometry, a clock is not a witness to a universal flow. It is an instrument that measures the length of one specific path through the four-dimensional structure of space-time, the particular path taken by the object the clock happens to be attached to. Physicists call this measured quantity proper time, and the word proper here is being used in an old-fashioned sense, meaning belonging to, particular to, this specific traveller's own route. A clock, in other words, is not a rain gauge, it is an odometer. This distinction sounds abstract until you follow through what it implies. An odometer in a car does not measure some universal quantity called distance that every car in the world shares. It measures the specific length of the specific route that specific car actually drove. Two cars can leave the same city on the same morning, arrive at the same distant city that evening, and register wildly different mileage because one took the direct highway and the other wandered along a scenic coastal road. Nobody finds this puzzling. Nobody argues that one odometer must be broken because it disagrees with the other. Both are correctly reporting the length of the particular path each car actually took. A clock on the Minkowski picture works exactly the same way, except the route in question is a path through space-time rather than a path across a map, and the length being measured is proper time rather than distance. Two travellers can begin at the same event, in the same place, at the same moment, separate, take different routes through space-time, and later reunite at a second shared event. And their clocks can disagree about how much time elapsed for each of them along the way. For precisely the same reason two odometers can disagree. They took different paths. Neither clock is malfunctioning. Neither traveller is somehow experiencing a different rate of universal time flowing past them. Each is correctly reporting the length of their own particular journey. Measured in the particular direction the geometry sets aside for that purpose. What makes this genuinely strange, rather than merely a clever analogy, is the specific shape of the rule governing how these path lengths are calculated, the minus sign we introduced back in part 3. In ordinary geometry, on a flat map, every detour from a straight line adds distance. There is no way to wander off course and come out with a shorter route than the direct path would have given you. Space-time, because of that minus sign sitting in front of the space terms, works in the opposite way. Motion through space subtracts from the proper time accumulated along a path rather than adding to it. A traveller who sits perfectly still between two events accumulates the maximum possible proper time available between those two events. Any traveller who moves through space in getting from one event to the other, any detour at all, arrives having accumulated less proper time, not more. The straight, motionless path is not merely one option among many. It is the longest possible route in the very specific sense that matters to a clock, and every deviation from it shortens the journey as measured by an odometer riding along. This is the entire mechanism behind what is popularly and slightly misleadingly called time dilation, a phrase that suggests something is being stretched or damaged, when what is actually happening is nothing more dramatic than two odometers correctly reporting two different route lengths. A clock carried through space at high speed is not malfunctioning, is not being physically squeezed or slowed by some external force acting on its gears. It is simply taking a longer route through space and, by the strict accounting of the geometry, a correspondingly shorter route through the dimension a clock is built to measure. Nothing is being lost. Nothing is being damaged. A different path was taken, and the odometer is reporting that path's true length, exactly as it should. The genuinely remarkable thing about this claim, the thing that separates it from an appealing analogy and turns it into hard science, is that it has been tested directly, repeatedly, with real clocks, and it has passed every single time. Begin with a population of subatomic particles that has no business surviving its own journey at all. Cosmic rays striking the upper atmosphere, roughly 15 kilometers above your head. produce a shower of particles called muons, heavier cousins of the electron, and muons are unstable. Left at rest in a laboratory, a muon decays, on average, in about 2/millionths of a second, a figure measured with extraordinary precision, because muon decay is one of the best characterized processes in particle physics. Even traveling at very close to the speed of light, a particle with that shorter lifespan should, by ordinary reckoning, cover only a few hundred meters before disintegrating. 15 kilometers of atmosphere should be, for the overwhelming majority of muons produced up there, an impossible distance to cross. And yet muons arrive at the ground, and not in some trickle explainable by rare statistical outliers, but in enormous, measurable numbers, hitting a patch of ground the size of your outstretched hand at a rate of roughly 1 per second. The explanation is exactly the mechanism this part has been building. From the muon's own reference frame, riding along its own path through space-time, its internal clock, the process governing its own decay, ticks along completely normally, exactly as any muon's clock always does. But that muon has taken a route through space at extraordinarily high speed. And by the geometry we have just laid out, a route through space subtracts from the proper time available for the journey. The atmosphere the muon has to cross, from its own accounting, is not 15 kilometers at all, but a distance contracted down to a small fraction of that, easily crossed within an ordinary muon lifetime. From the ground-based perspective, the explanation is phrased the other way around, in terms of the muon's own clock running slow relative to ours, ticking so much more slowly that even its brief 2-microsecond lifespan stretches out to cover the full descent. Both descriptions are correct. Both agree, down to the precise numbers, on how many muons should reach the ground. And both have been confirmed experimentally since the early 1940s, when physicists first carried detectors up a mountain in New Hampshire specifically to measure how the muon population thinned out with altitude, and found it thinning far more slowly than a naive, non-relativistic calculation predicted, and precisely in line with what the geometry demanded. This effect does not require exotic particles moving near the speed of light to become measurable. It has been directly measured using ordinary human technology, flown by ordinary human pilots on ordinary commercial flights. In October of 1971, two physicists working at the United States Naval Observatory, Joseph Hafele and Richard Keating, purchased commercial airline tickets for 4 cesium beam atomic clocks, strapping them into paid passenger seats and flying them, first eastward and then westward, all the way around the world, before comparing their readings against a set of reference clocks that had remained on the ground the entire time. The predicted discrepancies, combining the effect of the aircraft's speed with the effect of its altitude, were tiny, measured in mere billionths of a second, and yet the clocks that flew eastward returned reading measurably less elapsed time than the ground clocks, while the clocks that flew westward returned reading measurably more, exactly matching the direction and magnitude the geometry predicted, confirmed to within the experiment's margin of error. 4 ordinary clocks, given airline seats, had taken different routes through space-time, and their odometers reported it faithfully. And this is not merely a laboratory curiosity confined to particle accelerators and specially chartered flights. It is happening, right now, to human beings who have spent enough time moving fast enough for the effect to add up into something genuinely measurable across an entire career. Astronauts and cosmonauts who accumulate months and years aboard orbiting spacecraft, traveling at several kilometers per second relative to the ground, are, by the time they return home, measurably younger than they would have been had they simply stayed on Earth, not in some symbolic or approximate sense, but by a precisely calculable number of milliseconds, accumulated exactly according to the same formula that governs the muons and the airline clocks. The amounts involved are far too small for any human being to notice or feel. Nobody has ever returned from orbit and experienced their missing milliseconds as anything at all. But the number is not zero, and it has been checked by multiple independent methods against multiple independent kinds of clock, and it has never once come out wrong. What all of this means, taken together, is that the strange, almost poetic language we used in parts 3 and 4 to describe personal now moments sliced at different angles through space-time is not merely a philosophical flourish layered on top of the real physics. It is the real physics, made concrete, made measurable, made into a working part of the machinery that keeps global positioning satellites correctly synchronized with receivers on the ground. Machinery that would drift by kilometers within days if engineers simply ignored the fact that a satellite's clock, moving at orbital speed and sitting in a weaker gravitational field, takes a measurably different route through space-time than a clock sitting on your kitchen table. Every one of us, whether standing still, walking across a room, or flying across an ocean, is accumulating proper time along our own individual, unrepeatable path through the four-dimensional block, and every one of us is doing so at a slightly, almost immeasurably, but genuinely different rate than everyone around us, for the simple and now thoroughly tested reason that no two of us are ever taking quite the same route. There remains, however, a piece of this story we have carefully avoided until now, because it does not fit comfortably within special relativity at all, and requires an entirely different and considerably stranger extension of the geometry to explain properly. Everything covered so far has concerned motion through space, the effect of speed alone, in a universe with no gravity in it whatsoever. But gravity, it turns out, warps this same accounting even further, and does so in a way that connects the abstract geometry of space-time directly to something as ordinary and unavoidable as your own height. A clock sitting on the floor of a room ticks, however imperceptibly, at a different rate than a clock sitting on a shelf above it, and understanding why requires following Einstein from the flat, gravity-free spacetime of 1905 into the curved, mass-warped spacetime of his general theory of relativity, published a full decade later, in the middle of a war, after years of what Einstein himself later described as the most exhausting and difficult intellectual struggle of his life. That is where we are going next. Part 7. The Floor and the Shelf. In 1907, 2 years after publishing the paper that would eventually become known as Special Relativity, Einstein was still working at the patent office in Bern, and he later described what happened to him that year as the happiest thought of his life. He was sitting at his desk, thinking, as he so often did, about gravity, a subject his 1905 theory had conspicuously failed to touch. Special relativity handled motion beautifully, but only for observers moving at constant, unchanging velocity, gliding along in what physicists call inertial frames. It said nothing about acceleration, and it said nothing at all about the force that Newton had described so successfully 2 centuries earlier. The invisible pull that holds the moon in its orbit and drops an apple from a tree. And then, as Einstein told it later, a single image occurred to him. If a person falls freely, he realized, they will not feel their own weight. A person falling from a rooftop, for the brief duration of the fall, experiences no sensation of gravity at all. They are, in every meaningful physical sense available to their own body, weightless. This observation sounds almost too simple to be the seed of anything important. and that is precisely what makes it so remarkable. Einstein pushed on the thought and arrived at something he called the equivalence principle, a claim that turns out to be one of the deepest and most productive ideas in the entire history of physics. Imagine two sealed rooms with no windows. In one room, sitting on the surface of a planet, you feel the ordinary pull of gravity holding your feet to the floor. In the other room, out in deep space, far from any planet or star, a rocket engine is firing steadily beneath the floor, accelerating the room upward at a rate that exactly matches the strength of gravity in the first room. Einstein's claim was that no experiment performed entirely inside either sealed room with no way of looking outside could ever distinguish between the two situations. A ball dropped in the gravity room falls to the floor. A ball dropped in the accelerating room also falls to the floor for the entirely mundane reason that the floor is accelerating up to meet it. From the inside, gravity and acceleration are not merely similar. They are, for any local experiment you could possibly run, indistinguishable. This equivalence, simple as it sounds when stated plainly, turned out to carry an enormous and completely unexpected consequence for time itself, and Einstein worked it out using nothing more than the tools of special relativity, years before he had finished building the full mathematical machinery of general relativity. Picture that accelerating rocket again, and imagine a beam of light entering through a small hole in the floor, travelling straight up toward the ceiling. Because the rocket is accelerating, by the time the light reaches the ceiling has picked up additional speed compared to when the light first entered at the floor. An observer at the ceiling, therefore, is moving away from the light source at the moment the beam departed, and moving somewhat faster still by the time it arrives, which means that observer will measure the light as stretched out, shifted toward longer, redder wavelengths compared to how it was emitted. This is a straightforward consequence of ordinary motion, nothing exotic about it at all. But the equivalence principle demands that whatever happens in the accelerating rocket must also happen, for identical reasons, in a room sitting still in a gravitational field. Light climbing upward through a gravitational field, therefore, must also be shifted toward longer wavelengths, an effect that came to be called gravitational redshift. And if light itself is affected this way, then something more fundamental must be happening to the rate at which time itself is passing at different heights within that gravitational field. A clock sitting lower down, deeper within the gravitational field, closer to the source of gravity, must tick more slowly than a clock sitting higher up, farther from that source, and the difference is not an illusion produced by the travel time of light signals between them. It is a genuine physical difference in the rate at which each clock accumulates its own proper time, exactly analogous to the difference in proper time accumulated by two clocks taking different routes through space that we established in the last part, except now the culprit is not relative motion at all, but the curvature of space-time itself, produced by the presence of mass. This is the point where Minkowski's flat, undistorted geometry of 1908 stops being sufficient, and Einstein needed something considerably more sophisticated to finish the job properly. It took him until 1915, working through years of what he later described bluntly as immense effort and considerable anguish, learning an entire branch of mathematics called differential geometry that had been developed decades earlier by mathematicians with no interest in physics whatsoever, before he arrived at the finished field equations of general relativity. The central claim of that theory, distilled down to its essence, is that mass and energy do not merely sit within space-time, exerting a mysterious pull across empty distance the way Newton had imagined. Mass and energy curve the very shape of space-time around them, and objects moving through that curved region are not being pulled by any force at all in the traditional sense. They are simply following the straightest available path through a geometry that has been warped, the way a marble rolling across a stretched rubber sheet curves toward a heavy ball resting in the middle, not because the ball reaches out and grabs it, but because the ball has reshaped the surface the marble is rolling across. Gravity in this picture becomes geometry rather than force, and the warping of space-time by mass affects the time direction just as thoroughly as it affects the three directions of space. A massive object, a planet, a star, does not simply curve the space around it in the way a sagging rubber sheet is easy to picture. It curves the time direction too, and the practical, testable consequence of that curvature is precisely the gravitational time dilation the equivalence principle had already hinted at back in that Bern patent office years earlier. Clocks closer to a mass run measurably slower than clocks farther away from that same mass. And this is not a subtle theoretical footnote confined to black holes and neutron stars. It has been measured directly, repeatedly, using instruments sitting well within reach of ordinary engineering. In 1976, physicists launched an atomic clock aboard a rocket called Gravity Probe A, sending it to an altitude of roughly 10,000 kilometers before it fell back to Earth, and compared its reading throughout the flight against an identical clock that had remained on the ground. The clock that spent time farther from Earth's mass, higher up where gravity's grip is weaker, ran measurably faster than the ground clock, exactly matching Einstein's prediction to a precision of better than 1 part in 10,000. And the effect is not confined to rockets and satellites. Either, in 2010, physicists at the National Institute of Standards and Technology performed a version of this experiment using 2 of the most precise atomic clocks ever built, connected by a length of optical fiber and separated in height by a mere 33 centimeters, roughly the height of a single stair step. Even across that almost absurdly small difference in altitude, the clock sitting slightly higher measurably outpaced the clock sitting slightly lower, exactly in line with the prediction. Your head, quite literally, ages at a faster rate than your feet, by an amount so vanishingly small across the height of an ordinary human body that no instrument built before the 21st century could ever have hoped to detect it. And yet it is there, real, measured, and completely unavoidable, a direct physical consequence of the fact that your head sits, ever so slightly, farther from the centre of the Earth's mass than your feet do. This is not a curiosity confined to physics laboratories chasing ever finer precision for its own sake. It is load-bearing infrastructure, quietly running underneath a piece of technology most people carry in their pocket every single day. The satellites that make global positioning systems function orbit the Earth at an altitude of roughly 20,000 kilometers, moving at speeds of several kilometers per second, and both of these facts, their speed and their altitude, affect their onboard clocks in opposite directions at once. Their orbital speed, exactly as the special relativity we covered 2 parts ago predicts, causes their clocks to run slightly slower than clocks on the ground. Their greater distance from the Earth's mass, exactly as the general relativity covered in this part predicts, causes their clocks to run slightly faster. The 2 effects do not cancel. The net result, worked out precisely by engineers who had no choice but to take both predictions with total seriousness, is that GPS satellite clocks gain roughly 38 microseconds every single day relative to identical clocks on the ground. A discrepancy that sounds trivially small until you realize that if it were left uncorrected, the accumulated timing error would cause your phone's positioning system to drift by several kilometers within a single day, and considerably farther within a week. The relativistic correction is not a theoretical afterthought bolted onto the system for the sake of scientific accuracy. It is baked directly into the satellite firmware, running continuously, correcting for a curvature of space-time that most of the people relying on it every day have never once been told exists. What all of this delivers, once you put the last two parts together, is a considerably richer and stranger picture than the one you started tonight's viewing with. There is no universal river of time flowing uniformly through the cosmos. There is, instead, an enormous collection of individual clocks, each one accumulating its own proper time along its own particular route through a four-dimensional structure that is not flat and featureless, but curved. Warped by every mass sitting within it, tilted by every relative motion passing through it. A clock on a mountaintop and a clock in a valley disagree, ever so slightly, about how much time has elapsed between the same two events, for exactly the same underlying reason that a clock on an aeroplane and a clock on the ground disagree, and for exactly the same underlying reason that Hathaway and Keating's four cesium clocks disagreed with each other after circling the planet in opposite directions. Every one of these disagreements is real. None of them requires any of the clocks involved to be malfunctioning. Each is simply, faithfully, correctly reporting the proper length of its own particular journey through a structure that has never once, at any point in this story, contained anything resembling a uniformly flowing river for any of them to be swept along by. And this brings us, at last, to the question that has been quietly waiting underneath everything covered tonight. The question this entire video is named for. If the geometry contains no flow, and the thermodynamic arrow explains only the direction of the asymmetry rather than any sensation of motion through it, and every clock in the universe is simply measuring the length of its own individual path rather than reading off ticks from some shared universal metronome, then what, if anything, is the universe actually doing at the largest possible scale when we casually say that time is passing? Is there any sense in which the cosmos as a whole can be said to have an age, a history, a story unfolding, given that we have just spent the better part of an hour establishing that no single moment, no single now, is shared by every observer within it? The honest answer turns out to require one final careful distinction between the age assigned to the universe by cosmologists and the personal, individual, endlessly varied proper time accumulated by every single object living inside it. A distinction that reveals, in its final form, exactly how strange and exactly how quietly reasonable the answer to tonight's central question actually is. Part 8. The age that belongs to nobody in particular. You have almost certainly heard the number before, repeated so often in documentaries and textbooks that it has taken on the flat, unquestioned authority of a fact like the boiling point of water. The universe is 13.8 billion years old. It appears on posters, in museum exhibits, in the opening minutes of nearly every piece of popular cosmology ever produced, including, if we are being honest with each other tonight, videos not unlike this one. And after everything covered across the last 7 parts, that number ought to strike you as considerably stranger than it usually does, because we have just spent the better part of 2 hours carefully, patiently, methodically establishing that there is no universal clock, no shared present moment, no single flow of time that every observer in the cosmos experiences together. So what precisely is being measured when someone confidently states the universe's age down to 1/10 of a billion years? The honest answer is that the number is not a measurement of the universe in any absolute, observer-independent sense at all. It is a proper time, Exactly the quantity we spent parts 6 and 7 learning to take seriously, belonging to one very specific, carefully defined, entirely hypothetical traveller. Cosmologists call this traveller a comoving observer, and the definition is precise, even though the traveller themselves has never actually existed. A comoving observer is someone who has been at rest relative to the overall average distribution of matter in the universe since the very beginning, drifting along with the general cosmic expansion rather than moving through it in any additional direction, never once accelerating, never once taking a detour, following the straightest, simplest possible path available within the curved, expanding geometry of the cosmos. 13.8 billion years is the proper time that would have accumulated on this single, idealized, never actually realized observer's wristwatch, counted from the earliest moment the theory can meaningfully describe all the way up to now. Nobody has ever been that observer. Not you, not the Earth, not the Sun, not the Milky Way galaxy itself. Every single one of us has been in motion relative to that idealized cosmic average, orbiting, falling, accelerating, taking countless small detours through the curved four-dimensional structure of space-time. And every one of those detours, exactly as we established with the muons and the airline clocks and the astronauts back in part 6, costs proper time rather than adding it. The straight, undetoured path is the longest one available, and none of us has walked it. Which means, stated plainly and without exaggeration, that you personally are not 13.8 billion years removed from the beginning of the universe in the same sense a comoving observer would be. You are younger than that idealized figure by some genuinely calculable, if practically negligible, amount, accumulated across every orbit the Earth has taken around the Sun, every orbit the Sun has taken around the galactic centre, every bit of relative motion your entire lineage has ever undergone since matter first began condensing into the structures that eventually produced you. This is not a criticism of cosmology, and it is not an attempt to undermine a number that remains one of the genuine triumphs of modern physics, built from an extraordinary convergence of independent evidence, the expansion rate of the cosmos, the composition of the oldest stars, the precise pattern of warmth and coolness printed across the faint microwave glow left over from the early universe. The number is real, it is well established, and it plays an essential working role in cosmology. What it is not, and what this entire evening has been quietly building towards showing you, is a universal fact about the age of everything, shared identically by every observer, every particle, every galaxy within the cosmos it describes. It is, like every other clock reading covered tonight, a proper time, belonging to one specific, carefully chosen path through space-time, and the moment you understand that, an entire class of questions that sound deeply confusing on first encounter suddenly resolve themselves with startling clarity. Consider, for instance, one of the more genuinely disorienting facts in modern cosmology, one that trips up newcomers to the subject constantly and which makes complete sense the instant you stop assuming a single shared cosmic clock. The most distant galaxies astronomers can observe, captured by instruments like the James Webb Space Telescope peering back toward the very early universe, are commonly described as being over 13 billion light-years away. And yet the universe itself, cosmologists will also tell you in the same breath, is only 13.8 billion years old. If light from those galaxies has been travelling for roughly that entire span of cosmic history to reach us, how can the actual present-day distance to those same galaxies, once you account for the ongoing expansion of space during the light's long journey, be measured today at something closer to 30 billion light-years or more? The apparent contradiction dissolves completely once you recognize that distance, exactly like simultaneity back in part 2, is not a fixed, observer-independent quantity either. It depends entirely on which moment, whose now, you are choosing to measure it at. And in an expanding universe with no single universal present moment to anchor the measurement to, different well-defined ways of asking how far away is that galaxy produce entirely different, entirely legitimate numbers, none of them wrong, each one simply answering a subtly different version of the question. This same careful distinction resolves a puzzle that troubles a great many thoughtful people encountering cosmology for the first time. The question of what, if anything, existed before the beginning. It is an entirely natural question to ask, and it is asked constantly, and the honest, complete answer requires exactly the vocabulary this evening has spent so long building. The number 13.8 billion years is not describing a point in some larger, pre-existing span of time that the universe simply started partway through, the way a marathon starts at some particular clock time within an ordinary day that continued both before and after the starting gun. It is describing the full extent of the moving proper time available at all, the entire length of the specific path we have been discussing, measured from one end to the other. Asking what happened before the beginning of that path is, in a very precise sense, closer to asking what lies north of the North Pole, a question that sounds meaningful because the everyday grammar of before and after, north and south, is built entirely around situations where those directions extend indefinitely in both directions. At the earliest moments the theory can currently describe that assumptions simply may not hold, and modern physics, being honest about the limits of what it currently knows, generally declines to claim a confident answer about what, if anything, the concept of before even means at that boundary, rather than papering over the uncertainty with false confidence. What this part has been building toward, and what tonight's entire journey has been slowly assembling piece by piece since the very first minute, is a genuinely complete answer to the question this video is named for, and it is worth stating now plainly, with every piece of the argument sitting visibly underneath it rather than asserted on its own. The universe does not experience time the way you think, because the universe, taken as a single unified whole, does not experience time at all, not in the sense of possessing one shared, ticking, universal clock that every object and every observer within it reads off together. What exists instead, and what every part of tonight's journey has been demonstrating from a different angle, is a single four-dimensional structure, the block first described by Minkowski in that Cologne lecture hall in 1908, containing every event that has ever happened or ever will happen, laid out together with equal reality, sliced into past, present, and future differently by every different observer moving through it at every different velocity, exactly as the lightning strikes on the train demonstrated back in part 2. Within that structure, there is a genuine, physically real, statistically overwhelming arrow, not built into the geometry itself, but into the extraordinarily improbable low-entropy state the entire structure happened to begin in. An arrow strong enough to explain why memory only ever points backward. Why cause reliably precedes effect, why cups shatter and never unshatter, exactly as Part 5 demonstrated in careful, patient detail. And moving through that structure, along their own individual, unrepeated paths, are an uncountable number of clocks, each one, from the muons in the upper atmosphere to the cosmonauts returning from months in orbit to the very hairs on top of your head compared with the soles of your feet, accumulating its own proper time, measured along its own particular route, agreeing with no other clock's reading except by the barest of coincidences, and every one of those disagreements, checked and rechecked across nearly a century of increasingly precise experiments, has never once come out wrong. There is no flow, there never was one. What there is instead is shape, an intricate, curved, endlessly varied four-dimensional shape, carrying within it every moment anyone has ever lived or will ever live, tilted at a slightly different angle for every single traveller who has ever moved through it, and stitched together, end to end, by an arrow of increasing disorder so overwhelming in its statistical certainty that it produces, in creatures built the way you happen to be built, the unshakable, vivid, entirely convincing sensation of a single moment sweeping forward through a story that is, underneath that sensation, already complete. Somewhere in that structure, at this exact coordinate along your own particular path, unrepeatable, unshared in its precise details with any other observer who has ever lived, is you, reading these words, feeling with total conviction that this is happening now. It is. It also always will be, laid into the block exactly where it has always been, waiting. In whatever sense that word can still mean anything once you have taken the geometry seriously enough, for absolutely nobody, because there was never anything sweeping toward it in the first place. There was only ever the shape, and you tracing a small, warm, temporary thread of increasing disorder through the one small corner of it you happen to call a lifetime. Part 9. The equation with no clock in it. Everything covered so far tonight, the tilting light cones, the curved geometry of general relativity, the entropy gradient running through the block, belongs to what physicists sometimes call classical physics, the description of the universe that works magnificently at the scale of planets, stars, galaxies, and falling apples. There is another branch of physics, developed largely across the same decades Einstein spent building relativity, that governs the universe at its smallest scales, the behavior of electrons, photons, and atoms, and it is called quantum mechanics. And when physicists tried, across the middle decades of the 20th century, to bring these two extraordinarily successful theories together into a single unified description, something went wrong with time itself, in a way stranger than anything covered so far tonight, and stranger, frankly, than most popular accounts of physics ever admit. To understand why, you first need to understand what quantum mechanics actually does with time, because it treats time very differently than general relativity does, and the difference between the two turns out to be the seed of a problem physicists have been quietly wrestling with for over half a century. In general relativity, as we established in Part 7, time is not a fixed backdrop, it is part of the dynamical geometry itself, something that curves and warps in response to mass and energy, every bit as flexible and every bit as physical as the three dimensions of space. In quantum mechanics, by contrast, time plays an oddly privileged, almost old-fashioned role. It is treated as a fixed external parameter, a steady background against which the quantum state of a system evolves according to a specific equation. Developed in the 1920s by the Austrian physicist Erwin Schrödinger, an equation that describes how the probabilities associated with a quantum system change from one moment to the next. Crucially, in Schrödinger's equation, time is not a dynamical quantity being described by the theory. It is simply given, assumed, external, exactly the kind of fixed ticking. Newtonian-style clock that special relativity had already dismantled decades earlier, and that general relativity had gone even further to dissolve into flexible geometry. For most practical purposes, this mismatch causes no trouble at all. Quantum mechanics works extraordinarily well describing atoms, electrons, and photons, none of which involve gravity strong enough to matter. General relativity works extraordinarily well, describing planets, stars, and galaxies, none of which require any serious quantum treatment. The two theories, in their respective domains, are among the most successful and precisely tested pieces of science ever produced. And for the overwhelming majority of physical situations anyone will ever need to describe. You never need both of them working together at once. But there are situations, at least in principle, where you do need both simultaneously, situations involving enormous mass or energy concentrated into an extraordinarily small region, exactly the sort of conditions found at the center of a black hole, or, more relevantly for the story this video has been telling, at the very beginning of the universe itself, in the fraction of an instant before the whole of space had expanded to any appreciable size at all. To describe those conditions properly, physicists need a single theory that treats gravity the way general relativity does, as curved dynamical geometry, while simultaneously treating that geometry with the probabilistic, quantum mechanical rules that govern everything at the smallest scales. This unification, generally called quantum gravity, has been one of the central unsolved problems in theoretical physics for the better part of a century, and one of the strangest and least publicized difficulties that arises the moment physicists try to build it is that time itself. The very thing this whole video has been trying to properly understand seems to disappear from the equations almost entirely. The clearest and most famous illustration of this comes from an equation developed independently in the 1960s by the American physicist Bryce DeWitt, building on earlier work by John Wheeler, and known ever since as the Wheeler-DeWitt equation. It is, in essence, an attempt to write down the quantum mechanical version of general relativity, applying the logic of the Schrödinger equation not to a small system like an electron, but to the geometry of the entire universe itself. And when DeWitt actually wrote the equation out, working through the mathematics with the same careful rigor Einstein had applied to his own field equations decades earlier, he discovered something that startled him and has startled essentially every physicist who has encountered it since. The equation contains no time variable whatsoever. There is no ticking clock anywhere in its structure, no parameter representing the passage of moments, nothing playing the role that time plays in Schrödinger's ordinary quantum mechanics. The wave function this equation describes, representing in some sense the entire quantum state of the universe, does not evolve. It does not change from one moment to the next, because the equation contains no next for it to change into. It simply is a single static, unchanging mathematical object, describing all at once everything that could be said about the universe's geometry, with nothing resembling the flow of time built into it anywhere. This result is sometimes called, with a certain dry humour among physicists, the problem of time in quantum gravity, and it is worth being precise about what makes it different from everything else covered tonight. The relativity of simultaneity from Part 2 showed that different observers slice a shared four-dimensional block differently, disagreeing about which distant events count as simultaneous. But every observer still agreed that time, as a direction, was genuinely there in the structure, genuinely something to be sliced. The Wheeler-DeWitt equation raises a considerably more radical possibility. Perhaps, at the deepest level physics has yet been able to probe, there is no time direction there at all, not merely one that different observers disagree about slicing, but one that may not exist as a fundamental feature of reality in the first place. If this equation, or something like it, correctly describes the universe at the level where quantum mechanics and gravity genuinely meet, then time itself may not be woven into the basic fabric of existence the way space is. It may be something else entirely, something that only appears, only becomes meaningful once you step back from the most fundamental description and start looking at larger, more complex structures built out of that timeless foundation. If that sounds abstract to the point of uselessness, there is a genuinely elegant proposed resolution developed initially in 1983 by the physicists Don Page and William Wooters that gives this timeless picture a concrete, almost intuitive mechanism, and it is worth walking through carefully because it offers one of the most satisfying answers available anywhere in physics to the question this entire video has been circling. Page and Wooters asked what would happen if you took the Wheeler-DeWitt equation's timeless, unchanging universal wave function completely seriously, and then asked how an observer embedded within that universe, itself part of the same unchanging quantum state, could nonetheless experience something that felt like the passage of time. Their answer hinges on a genuinely strange and thoroughly experimentally confirmed feature of quantum mechanics called entanglement, the phenomenon by which two quantum systems can become correlated with each other in a way that has no equivalent anywhere in classical physics, such that measuring a property of one instantaneously tells you something definite about the corresponding property of the other, no matter how far apart they happen to be. Page and Wooters proposed that time, as experienced by any observer, is not a fundamental background feature of the universe at all, but an emergent property arising entirely from the pattern of entanglement between different parts of an otherwise static, timeless whole. Imagine the universe's total, unchanging quantum state as containing within it both a clock, in the broadest possible sense of the word, some subsystem whose configuration correlates with change, and the rest of the universe, everything an observer might want to measure. The overall state of clock plus universe together in the Page-Wooters picture is static and eternal, exactly as the Wheeler-DeWitt equation demands, with no time variable anywhere in its description. But because the clock subsystem is entangled with the rest of the universe, different possible readings on that clock correspond to different, distinct configurations of everything else, and an observer who is themselves part of that entangled system, who can only ever access information relationally, by comparing one part of the whole to another rather than viewing the whole from some impossible external vantage point, experiences those different clock-correlated configurations sequentially as a felt passage of time, even though the total underlying state they are embedded within never changes at all. This is a genuinely difficult idea to hold in your head, and it is worth admitting plainly that it remains a proposed resolution rather than a settled, universally accepted fact. One live and actively debated theoretical framework among several competing approaches to the problem of time in quantum gravity, none of which has yet been experimentally confirmed in the way the muon decays and the atomic clocks covered earlier tonight have been. But the picture it offers is worth sitting with regardless, because it takes the strangest thread running through this entire video, the idea that time might not be a flow at all, but something built out of relationships between different parts of a larger structure, and pushes it one step further than anything covered so far. It suggests that even the block universe itself, timeless and complete as Minkowski described it, might not be the final, most fundamental layer of reality, but might itself be something that emerges. The way temperature emerges from the statistical behavior of enormous numbers of individual molecules, from an even deeper, even stranger foundation in which the concept of time in any form at all genuinely does not apply. There is a small, quiet piece of experimental progress worth mentioning here, because it keeps this from remaining purely a matter of untestable philosophy. In 2013, a team of researchers led by the physicist Ekaterina Moreva, working at the Istituto Nazionale di Ricerca Meteorologica in Turin, constructed a small laboratory analogue of the Page-Wooters mechanism using pairs of entangled photons, arranging one photon to serve as the clock subsystem and the other to serve as the observed universe, and demonstrating in a controlled, repeatable optical experiment that an observer with access only to the correlations between the two photons and no access to any external absolute time reference would indeed perceive the kind of relational, emergent evolution the Page-Wooters proposal predicts, while an observer with access to the full, unentangled system would correctly see no evolution at all. It is a small experiment involving nothing more exotic than photons and optical benches, and it does not by any means prove that the universe as a whole works this way. But it demonstrates that the mechanism Page and Wooters proposed is not merely a mathematical curiosity confined to inaccessible equations describing conditions at the birth of the cosmos. It is, at least in miniature, a real, physically demonstrable phenomenon, sitting quietly at the intersection of quantum entanglement and the felt experience of time passing, and it stands as one of the more remarkable, underappreciated pieces of evidence that the question this entire video has been asking, what is the universe actually doing when we say time is passing, may have an answer considerably stranger and considerably deeper than anything the classical geometry of relativity alone could ever have suggested. Part 10. The garden that has no gardener. There is a particular kind of vertigo that sets in once you have spent long enough sitting with the ideas covered so far tonight, and it usually arrives in the form of a single, simple, almost embarrassingly direct question. If the universe really is a single timeless block, with past, present, and future all equally real, laid out together the way pages already sit within a finished book, then what precisely is choosing to happen next? Every decision you have ever made, every branch your life has taken, feels, from the inside, like an open choice made in a genuinely undetermined moment. The block universe seems to say that this feeling, vivid as it is, describes nothing real, that the choice was never actually open in any meaningful sense, because the outcome was already sitting there, fixed, in the block, before you ever felt yourself deciding anything at all. This is where the physics covered tonight starts brushing up against questions that are not, strictly speaking, physics questions anymore. And it is worth being honest and careful about exactly where that boundary sits, rather than pretending the equations settle a debate that philosophers have been having, in one form or another, for over 2,000 years. The philosophical position this worry points toward is usually called determinism, the idea that the state of the universe at any one moment fixes, completely and without exception, the state of the universe at every later moment, leaving no room anywhere for anything to have gone differently. Determinism did not originate with relativity. It is far older, tracing back at least to the mechanical, clockwork universe Newton's own laws of motion seem to describe centuries earlier, a universe in which, in principle, a sufficiently powerful calculating intelligence, given complete knowledge of every particle's position and velocity at a single instant, could predict every future event and retrodict every past event with perfect accuracy. A thought experiment famously described by the French mathematician Pierre-Simon Laplace in 1814, and which has come to be known ever since as Laplace's demon. What relativity and the block universe add to this considerably older worry is not the worry itself, but a particular, vivid, geometric image of it, a universe not merely governed by deterministic laws unfolding through time, but one in which past and future are already there together, removing even the metaphorical sense in which the future might be described as not yet decided. It is worth being genuinely careful here, because there is a real difference between what the physics actually establishes and what people sometimes assume it establishes, and collapsing that distinction does a disservice to both the science and the philosophy. Special and general relativity, as covered across the earlier parts of tonight's video, are entirely compatible with a deterministic universe, and the block universe picture fits that compatibility naturally. But relativity on its own does not, strictly speaking, require determinism, and quantum mechanics, the other great pillar of 20th century physics introduced in the previous part, complicates the picture considerably. At the smallest scales, quantum mechanics does not predict single definite outcomes for most physical processes. It predicts probabilities, a spread of possible results, with the specific outcome of any individual measurement genuinely, fundamentally unpredictable in advance. Not merely unpredictable because of some hidden information nobody has yet uncovered, but unpredictable in a way that the overwhelming majority of working physicists take to be a basic, irreducible feature of reality itself. This is not a fringe or minority interpretation. It follows directly from decades of experiments testing something called Bell's theorem, developed by the physicist John Stuart Bell in 1964. Which showed that no theory relying on hidden but already determined information, sitting quietly beneath the quantum probabilities waiting to be uncovered, could reproduce the specific statistical patterns quantum mechanics predicts and that experiments, refined with extraordinary care across the following decades and honoured with the Nobel Prize in Physics in 2022 for work closing the last. Major loopholes in these tests have repeatedly, consistently confirmed. So how does this square with the block universe, a structure in which the future appears to sit already fixed alongside the past? The honest answer is that this remains one of the genuinely open, actively debated questions at the foundations of physics. Not a settled matter with a single agreed answer waiting to be handed to you at the end of a video. One broad family of interpretations, sometimes grouped loosely under the heading of the many worlds interpretation, first proposed by the physicist Hugh Everett in 1957, suggests that quantum indeterminacy is fully compatible with a timeless deterministic block, because every possible outcome of every quantum event actually occurs, each one branching off into its own separate, equally real region of a far vaster structure than the single block universe describes, with the felt experience of genuine open uncertainty arising simply from the fact that any given observer only ever experiences one branch among the enormous, ever multiplying many, unable from the inside to tell that the others exist at all. Another broad family of interpretations takes quantum indeterminacy considerably more literally, suggesting that the future, at least at the quantum level, genuinely is open and undetermined until measurement occurs, which would mean the block universe picture, strictly speaking, cannot extend all the way forward through cosmic history in the fixed, complete way Part 4 described, but must instead resemble something closer to the growing block view mentioned back in that same part, with the past and present settled and fixed, but the future genuinely physically open, growing moment by moment as quantum outcomes crystallize into definite fact rather than sitting already, determined and simply awaiting discovery. Neither of these positions, nor the several other serious alternatives physicists and philosophers have proposed across the decades, has been settled by experiment in the way the muon lifetimes and the atomic clock discrepancies covered earlier tonight have been settled. This is worth dwelling on for a moment, because it stands in genuine, honest contrast to nearly everything else in this video. The relativity of simultaneity, the gravitational slowing of clocks, the entropy gradient explaining the arrow of time, all of these rest on results confirmed by repeated, independent, carefully controlled experiments, checked against each other across nearly a century of increasingly precise technology, and none of them are seriously disputed by working physicists. The deeper question of whether the universe, at the most fundamental level, is deterministic or genuinely open, whether the future already sits fixed within the block or remains, in some physically meaningful sense, still being written, has not received that same kind of decisive experimental answer. And it may be, given the peculiar difficulties covered in the previous part concerning quantum gravity and the apparent disappearance of time from the deepest equations physicists have yet written down, that no experiment currently conceivable could settle it. What can honestly be said, and what is worth holding on to as tonight's journey moves toward its final stretch, is this. Nothing in the physics covered across this entire video, not the light cones, not the curved geometry of general relativity, not the entropy gradient, not even the deeply strange, still developing picture of quantum gravity covered in the last part, requires you to conclude that your choices are meaningless, or that the felt sense of deliberation, of weighing one option against another and genuinely settling on one, is some kind of trick your brain is playing on you. What the physics does require, and this is different from that stronger, more alarming claim, is that you give up the assumption that this felt sense of open deliberation corresponds to a universal, shared, currently being decided present moment sweeping forward through the cosmos on behalf of everyone at once. Whatever is happening when you deliberate and choose, and it is a genuine, physically real process, involving genuine, physically real complexity in the arrangement and interaction of the matter making up your brain. It is happening along your own particular path through the four-dimensional structure this video has spent 10 parts carefully describing, and it is entangled, in ways covered in the previous part, and in ways still being actively worked out by physicists and philosophers together, with the deep, still partially mysterious question of what time itself most fundamentally is. The vertigo does not fully resolve. It was never going to, not in a single evening, and probably not in a single human lifetime of careful thought. But it is, at the very least, now a vertigo built on an honest, carefully examined foundation, rather than one built on the comfortable but thoroughly dismantled assumption of a single universal clock ticking the same way for everyone, everywhere. That this entire video began by taking apart. Part 11. The particle that keeps its own diary. There is one more piece of evidence worth adding to everything covered so far tonight, because it does something the earlier examples did not quite manage. The muons and the airline clocks and the astronauts all demonstrated that proper time, the length of an individual path through space-time, is a real, measurable quantity that differs from one traveller to the next. But all of those examples still involved something recognizably clock-like, an oscillation, a decay rate, a mechanical process ticking along in the ordinary sense of the word. There is a stranger and in some ways more persuasive category of evidence, drawn from the physics of entangled particles. That shows the geometry of space-time shaping the relationships between distant events directly, without any clock in the traditional sense involved at all, and it is worth walking through carefully, because it closes a gap that a careful listener might reasonably still feel sitting open after everything covered so far. Quantum entanglement, introduced briefly in Part 9, is one of the most thoroughly tested and least intuitive phenomena in the whole of physics. When two particles become entangled, typically through some shared interaction at the moment they are created, they end up in a joint quantum state such that measuring a property of one particle instantaneously determines the corresponding property of the other. no matter how far apart the two particles have since travelled. Einstein himself, together with two collaborators, Boris Podolsky and Nathan Rosen, raised this phenomenon as an objection to quantum mechanics in a paper published in 1935, arguing that any theory permitting this kind of instantaneous correlation across arbitrary distances must be incomplete, must be missing some hidden, already determined information that would restore a sensible, local picture of reality if only physicists could uncover it. Einstein referred to the phenomenon, dismissively, as spooky action at a distance, and it is a measure of how strange this corner of physics is that the very theorist who dismantled the universal present moment found this particular consequence of quantum mechanics a step too far to accept. The experiments that eventually settled the argument, decades after Einstein's death, came down decisively against him. Bell's theorem, mentioned in the last part, showed precisely how to test whether the correlations between entangled particles could be explained by any hidden pre-existing local information, and the increasingly refined experiments conducted from the 1970s onward, culminating in the loophole closing tests honoured by the 2022 Nobel Prize, showed conclusively that they cannot. The correlations really are as strange as quantum mechanics predicts, and no amount of hidden local information sitting quietly inside the particles from the moment they separated can account for them. What makes this relevant to tonight's central question is what happens when you ask, carefully and precisely, whether this spooky action at a distance actually violates the causal structure established all the way back in Part 3, the light cone structure that Minkowski's geometry uses to protect cause and effect from the relativity of simultaneity. The answer, worked out with great care by physicists across the decades following the original Einstein-Podolsky-Rosen paper, is a genuinely elegant and reassuring no, and the reason why touches directly on everything this video has been building. Although measuring one entangled particle does instantaneously correlate with the state of its distant partner, that correlation cannot be used to send any actual signal, any actual usable information faster than light. The outcome of any individual measurement on an entangled particle is itself genuinely random, exactly the kind of fundamental quantum indeterminacy discussed in the last part, and it is only when the results from both distant measurements are later brought together and compared, a process that necessarily requires an ordinary light speed or slower signal travelling between the two locations, that the correlation becomes apparent at all. The light cone structure, the strict absolute boundary between events that can causally influence each other and events that cannot, remains completely intact. Entanglement produces a correlation that outstrips anything classical physics could explain, but it never produces a usable message that outpaces light itself, and this, careful, precisely enforced limitation is now known, somewhat dryly, as the no-communication theorem, proven rigorously within the standard mathematical framework of quantum mechanics, and never once violated in any experiment performed since. This matters enormously for tonight's story because it demonstrates something genuinely remarkable about how tightly the strange, probabilistic world of quantum mechanics and the strict geometric world of relativity actually fit together, despite the deep unresolved tensions covered in Part 9 concerning quantum gravity. Even in the one place where quantum physics seems, on first encounter, most likely to break the causal structure this entire video has been carefully protecting since the lightning strikes on the train back in Part 2, the geometry holds. Space-time's light cones do not merely describe an approximate everyday rule of thumb that breaks down under sufficiently strange quantum conditions. They describe something the deepest, most thoroughly tested corners of modern physics have gone out of their way, repeatedly to confirm rather than undermine. There is a further, genuinely useful piece of physics that grows directly out of this careful balance, and it brings tonight's discussion back in a satisfying way to the practical, technological world rather than leaving everything at the level of abstract principle. In 2023, a team led by the physicist David Arvidsson Shukur at the University of Cambridge, along with collaborators, published research demonstrating that carefully engineered quantum entanglement can be used to solve certain experimental problems that would be flatly, provably impossible to solve using only classical, non-entangled information travelling forward through time in the ordinary way. The team illustrated the underlying idea with a deliberately everyday analogy, imagining a situation in which you need to send someone a gift chosen specifically to match a wish list, but the wish list itself will not be available to you until after the gift has already needed to be sent. In an ordinary classical world, this is simply impossible, a straightforward violation of cause and effect. Using entangled particles carefully prepared and measured according to specific protocols, the team showed that certain classes of this kind of problem can, in a precise mathematical sense, be resolved as though information had been available earlier than it actually arrived, producing a measurable, useful, technological advantage in specific quantum sensing and metrology applications. It bears repeating clearly and without exaggeration, exactly as the researchers themselves were careful to state, that this does not involve literal backward in time signaling. No information travels from the future to the past in any of these experiments, and the light cone structure protecting causality remains, as always, completely intact. What the experiments demonstrate instead is that the correlations quantum entanglement makes available are rich and strange enough that certain problems which look, on the surface, like they require backward causation to solve, can in fact be solved using entirely forward-moving, entirely causality-respecting physics, provided you are willing to work with the full. Counterintuitive resources quantum mechanics actually provides rather than the more limited classical intuition most people, understandably, bring to problems involving cause and effect. Taken together, everything covered in this part adds a final important texture to the picture this video has been assembling since the very first minute. The universe, at its most fundamental level, currently accessible to experiment, is not merely a passive static block containing fixed events connected by rigid, unbending causal rules, nor is it a chaotic, anything-goes structure in which quantum weirdness has quietly dissolved the careful geometric boundaries relativity spent so long establishing. It is something considerably more interesting than either of those simpler pictures, a structure in which the strict geometric protection of cause and effect established by Minkowski's light cones coexists, in careful, precisely balanced tension, with a layer of quantum correlation stranger and richer than classical intuition was ever built to expect, a layer that experiments continue, year after year, to probe more deeply, and which continues so far to respect every boundary relativity insists upon, while simultaneously revealing that the boundary itself permits far more strangeness within it than anyone in 1908, watching Minkowski deliver that lecture in Cologne, could possibly have anticipated. So here is what the universe was actually doing this whole time. Not ticking, not flowing, simply being, whole and complete, a single vast shape with every moment you have ever lived already woven into it, tilted at its own private angle, connected to every other moment by threads of cause, entropy, and entanglement finer than anything Newton could have imagined. There is no clock behind the curtain. There never was. Only the shape, and you tracing one small warm thread of increasing disorder through the one corner of it you happen to call a life. You are lying there right now, certain this moment is happening. It is. It always will be, held exactly where it is, waiting for nobody, because nothing was ever sweeping toward it in the first place. If this changed how you feel about the word now, there is a whole galaxy of nights like this one waiting for you. Stay a while longer, subscribe, and let the next mystery find you exactly where this one did.